That's right. Okay, so this time, the time before, we were looking at um, how their politics break down along sex lines. Now we're going to do it the opposite way, how the different sexes differ based on the politics. So the question we're going to try and answer is, if you are a moderate, are you more likely to be male or female? So if you're going back to the original stuff, if you're a moderate, are you more likely to be a male or a female? This is what we're looking at. So let's come back to this. This time we're going down the table. We're looking at their politics. So of the liberals, 41% were female, 49% were male. Of the moderates, 45% were female, 55% were male. And of the conservatives, 22% were female and 78% were male. So note that in this class, if someone is a moderate, so they belong in here, then that student is more likely to be a male than female. Strangely enough, the same trend is true for political conservatives. If you're a conservative, you're more likely to be male than female. And interestingly enough, if you're liberal, you're more likely to be male than female in this particular class. Now, how in the world did that happen? Yeah, it's because there's more guys than girls in this class. There's 115 guys and only 77 girls. Okay, so sometimes you run into strange things like that. Okay, so also notice the 100s tell you which way to read this table. Where you've got these 100%, that tells you you're reading down these. Whereas up here, your 100% means you're reading across for these. Okay, so where the 100% are can tell you where. Now, occasionally, they won't put this on, and you're like, okay, I got to figure out which one of these is 100. Well, this is clearly not 100, it's only 88%. So add up going across, and I find that that's 100%. So we pointed this out yesterday, but remember that of is the key word. In the first table, we can see that of the males in the class, so that means males is the whole group we're looking at, 18% are conservative. So of the males, 18% are conservative. We're looking at this as a whole. And then of the conservatives in the class, 78% of them are male. So it's an important distinction, and it's really easy to get it backwards. So you have to read carefully on these. So we could display the information in the first conditional distribution table by dividing up bars rather than circles with one bar representing females and the other representing males. Here's what we're talking about. Turn the page, please. Should have printed these in color because I can, and for small runs it's not like it's that much more expensive to print in color. But now you have some lovely grayscale things to try and figure out what's what, which is the story of my brother's life. His color blindness is so bad he's almost monochromatic.
Like there's no colors that you see?
There's just not a lot. For a long time, his favorite color was black because that was the one he was sure of. It's like,
Yes.
that's black. Everything else, he was like, I don't know. He also needed glasses from a young age. And I can still remember the first time he wore them, and he was like, I didn't realize that there were like individual leaves on trees. I just thought it was this big. And really, I mean, that's how he saw. I'm like, what did you think the leaves on the ground were? And he's like, I wasn't really sure. Wow, okay. All right, so here we can see that the percentage of liberals is almost identical both for females and males, right? Meaning that being liberal is likely independent of sex. So that's an important idea. So the percentage of liberals is almost identical. And again, later on in this year, we'll have a way of testing that numerically, but that's not for a long time. So that means that being liberal is likely independent of sex, while being moderate or conservative is at least somewhat dependent on sex. So one limitation of segmented bar graphs or bar charts, I usually call them bar graphs, I don't know why, they call them charts, doesn't really matter, is that they do not show the sizes of the groups, right? There were way more males than females in this particular class. This doesn't show that. But a mosaic plot, which is nowhere to be found in your book because it's relatively new to the AP, does. So in our previous example, it was about 40% female and 60% male. That doesn't show up. So here's a mosaic plot for something. So on the left, we have a segmented bar graph that shows that approximately the same percentage of 25 to 34-year-olds as those 55 plus have an educational attainment of an associate's or bachelor's degree. So the associate's or bachelor's degree is this one, if I'm reading that correctly. Man, those. You think it's the orange? Is this orange? Man, that's small. Okay, so it's the orange one. So you can see that about the same percentage of those two groups have an associate's or a bachelor's degree. But it doesn't tell you that there were way more 55 plus people than there were 25 to 34, which if you think about 25 to 34 is only a 9-year span. 55 plus goes to 55 until you die, right? So especially in the United States in this day and age right now, with the baby boomers still being around, there's just an awful lot of them, right? And so although the percentage of each is about the same, there are way more people in this group that have an associate's or a bachelor's degree. So that's how you can read more from a mosaic plot than you can just from a segmented bar graph. Now, a segmented bar graph, I think, are great when the groups that you're looking at have about the same number of people in them, or about the same number of whatever it is in them. When they differ by quite a lot, a mosaic plot is better. Yes?
With the mosaic plot, will they always border each other? There'll never be a divide between them?
That's a really good question, and I think that's normally the way mosaic plots are done. They're normally smashed together. And I'm not sure why. I don't think I've ever really thought about that. Um, so like on this one, could we have smashed these together? Well, yeah, because there is no real gap between them, right? 25 to 34, 35 to 54, there's no gap between those. So, just as a note, and I think it's just what I just said, although this is an AP statistics topic, your book, and in fact many other books, don't have a particularly lot about it. We'll do another example of those later on when we do some examples from this chapter, and that'll be about it. But it showed up as an AP question, either not this last May, either the previous May to that or the one before that. I can't remember which. And all my students were like, yeah, no big deal. Okay? So I think once you're aware of what it is that it's showing you, it's pretty easy to understand. The bigger the area, the more people there are in this case, right? Or the more whatever there are. All right, so be careful about percentages across very different values or groups. So like when we looked at the political group, a student group is more likely to be male than female. You have to be careful about that because they weren't the same size group. People often assume that it's the same size group. You gotta be, this is one of those things to be leery about, okay? Overall averages can sometimes be misleading when the data comes from different sizes of groups. Let's look at this last part. Simpson's paradox. This is pretty cool. You're going to look at this and your eyes are going to cross for a minute, and then it's all going to kind of settle in, and you're like, oh yeah, we have to be careful about this. So let's take a look. It's the last inning of an important baseball game. You may argue, important baseball game? In the grand scheme of things, okay, but for the sake of this, we'll say it's important. Maybe not to you, but to someone. Your team is a rundown with the bases loaded and 2 outs. Your next batter is your weak hitting shortstop, so you, as the manager, will be sending in a pinch hitter. For those of you who don't follow baseball, the pinch hitter, basically you can substitute somebody in. There are all kinds of rules about that, but it's the end of the game. You're either going to at least tie it up, maybe win or lose. So there are 2 batters available on the bench. Whom should you send in to bat? Here are the players' summary records for the last 4 months of the season. That's a pretty good sized. You haven't looked at the whole season, but you're looking at the most recent 4 months. That may be too much, but it gives you an idea how they're doing. So, first of all, we're going to find their overall batting averages. So for Alvarez, the way you find batting average, it's just like finding a percentage, except you don't multiply by 100. Or do you multiply by 100? What do you multiply by? Well, let's see. If it's 33 out of 103, you multiply that by 1,000 to get the batting average. It's a 320 batting average. Why they didn't just leave it as .320, I don't know. Maybe that was too difficult for people to understand. But they get a hit about 32% of the time. So then Blyleven And for those of you who don't follow baseball, these are real baseball players' names. So if we do that, 45 for 151 is a 298. So if all you looked at was their batting average, who do you think you would choose? Alvarez. The question that ended in a period and should have been in a question mark is, does it matter whether the pitcher is left-handed or right-handed? Oh, maybe one of them is really good against left-handed and sucks against right-handed, or vice versa, and that might better inform me. Okay, so let's find the batting averages against those type of pitchers for each batter. So for LHP, that's left-handed pitcher, Alvarez's batting average it's 28 for 81. He's hitting 346 if you round it. That's pretty good. Let's see what Blyleven is hitting. He's 12 for 32. He's hitting 375. Oh. So if it's a left-handed pitcher, who might we want to pick? Blyleven. All right, let's see what happens if it's a right-handed pitcher. If we have a right-handed pitcher, for Alvarez, it's 5 for 22. He's hitting 227. Well, that's not great. Let's see about Blyleven. It's 33 for 119. That's 277. Blyleven hits better against left-handed pitchers and hits better against right-handed pitchers than Alvarez does. Seems weird, doesn't it? It doesn't feel like that should be possible. Wait a minute, how can he be better against both but not be better overall? So here's what happened. Both of them are worse against right-handed pitching, right? Who hit a bunch against right-handed pitching compared to the other one? Blyleven hit a bunch against right-handed pitchers. Alvarez, not so much. And since they're both worse against right-handed pitchers, that lowered his overall batting average. So this is why you have to be really careful about overall statistics if the individual parts aren't the same, right? Alvarez is better against left-handed pitchers, and he hit over twice as many times against left-handed pitchers than Blyleven did. This is what leads to this particular paradox. Is the overall numbers versus the individual. Okay, you'll see this in some of the homework. There's some great problems. There's one about, I want to say there's one about a hospital where they compare this hospital to this hospital. And they're like, which one should you go to? When you do the overall, it tells you one thing, but when you look at the specialties, one of them, the other one is actually better at both kinds of surgeries. Okay, so you have to be careful about reporting these overall statistics. So now I think that Blyleven is the better choice. So how did this happen? You can either go at it as, you know, they're both better against left-handed, but Alvarez got to feast on that more often than Blyleven did, or you can talk about they're both worse versus right-handed pitching, and Blyleven had to face right-handers about 5 times as many times. Okay? You can talk about it either way that you want to. I'll let you word that however you would like to. To give another sports analogy, in basketball, sometimes they'll talk about garbage time. So garbage time in a basketball game is one team is way ahead and they put in, you know, all their second stringers and stuff. The stats in garbage time bear no resemblance to what people's stats are overall. So if they played in, you know, primarily in garbage time, they may have gotten some easy buckets that they wouldn't have gotten in a real game. So you have to be careful about things like that when people will make claims. This is part of why what I tell students is anytime someone tries to convince you of something by giving you one statistic, they're almost always hiding something. They have figured out the statistic that makes whatever viewpoint they have look better. And this happens across the spectrum. It happens in the political arena. It happens in sports all the time. Any endeavor you want to name, someone will pick the one that makes their viewpoint look better. And you have to be careful about that. Now, sometimes people do it unwittingly. They don't know that they haven't looked enough. Sometimes people do it maliciously. They actually look and go, well, that one makes me look bad. I'm not going to share that. That makes me look bad. I'm not going to share that. Hey, this one makes it look like my idea is a good idea, or my candidate's a good candidate, or whatever. And then they ignore everything else. Context is important, and getting getting all the information, not just one thing. Okay? I saw a great one time about, you know how on Amazon and other different places, you know, they have, you know, reviews and it's how many stars or whatever. And there was one, and I can't remember the exact numbers, but, you know, whatever product, 5-star review, 5-star review, 5-star review, 5-star review, 1-star review, and you look at the 1-star review and you're like, it exploded the first time I used it, right? Well, the average came out to be, you know, 4.5 stars or something, because for most people it worked great. The fact that it exploded and, you know, blew out all the windows in the house and killed your dog, like, maybe you don't want to get that. So maybe just looking at the number of stars that it gets is not a good way to decide whether or not you want that product. You want more information than that. But we tend to be swayed by things like that. Okay, I'll give you another example. You know, Rotten Tomatoes, for example, what they do is it's strictly thumbs up, thumbs down, what's the average? Okay, so sometimes you can have a movie that has 87% thumbs up on Rotten Tomatoes. But if you actually look at the reviews, those were all tepid. You want to add that to your list? Do you know tepid? No, that's not what tepid means.
Mediocre based on context?
Lukewarm. If something is tepid, it is lukewarm. So, of those 87%, 80% of them were, it was okay. I'm going to give it a weak thumbs up, right? As opposed to some other movie that got, say, 83% less thumbs up, but the ones that were thumbs up were really enthusiastic. There's more to it than just that single number. And if you're making decisions, especially important decisions, which movie you see is not nearly as important, but when you're making important decisions, if you're making it based on a single number, it's almost always you haven't gotten enough information yet. Okay? One of the things that my dad always harped on was get as much information as you can, but don't drive yourself crazy with it either. He goes, get as much information as you can, make the decision, and move on. Which I thought was pretty good advice. Okay. I'll stop yammering at you at this point.